Ever find yourself glued to the Weather Channel, like when one of those hurricanes is brewing? You're not alone.
Not at all.
Today, we're diving deep, really deep, into the world of tropical cyclones.
Yeah.
And not just the hurricane coming, watch out kind of stuff. We're going for the real nitty-gritty, the science behind how these storms form, how they change, and even some surprising ways they affect our whole planet.
Definitely. It's fascinating stuff.
You sent over some really cool material from, of all places, Wikipedia about tropical cyclones.
Oh, yeah. Wikipedia. It's a treasure trove.
Lots to unpack.
Tons to unpack.
So before we get lost in the eye of the storm, let's start with the basics, shall we?
Absolutely.
The article, it mentions warm water being super important for these cyclones to even get started. But we're talking seriously warm here, like bath water warm.
Yeah, we're talking really warm water. It's got to be around, think about this, 81 degrees Fahrenheit.
81 degrees. It's like a
That's-
hot tub.
It's 27 degrees Celsius. And that temperature, it's like a magic number because it lets enough of that ocean water evaporate and then rise up into the atmosphere. But, and this is important, it's more than just what's happening at the surface. It's about the ocean's heat content. The total amount of heat that's stored in the water column, like way down. Think of it like the fuel tank for a cyclone.
So a bigger fuel tank, meaning a deeper reservoir of that warm water, equals a higher chance of a cyclone really gaining some power.
You got it. That's one of the key things behind what we call rapid intensification. That's when a cyclone goes from, kind of weak to batten down the hatches in practically no time.
Yeah, that's the scary part.
It is pretty scary.
Now, the article did mention that this whole rapid intensification thing, it's still a bit of a mystery even for scientists.
Yeah, it's true. We've got the basic ingredients for a cyclone to form down pat, but rapid intensification, that's complex. It's like trying to solve a puzzle, but you've only got half the pieces. One thing we know for sure, though, is that low wind shear plays a big part.
Wind shear.
Yeah, it's basically the change in wind speed or direction as you go higher up. When that wind shear is low, it lets the cyclone get its act together, develop a more organized structure, and bam, intensify super fast.
So low wind shear, it's like clearing the runway for a cyclone to become the Incredible Hulk of storms.
Perfect analogy. And just like there are those Goldilocks conditions for cyclones to even form, there are all sorts of ways they just kind of fizzle out. Sometimes they hit land and that's it, but other times they drift over colder water and, well, they basically run out of gas.
Makes sense. It's like they starve to death, these cyclones.
Exactly. They need that fuel.
Speaking of Goldilocks and cyclones, the article mentioned some of these storms are surprisingly tiny.
Yeah, size can be deceiving when it comes to cyclones. You got a recent example, Tropical Storm Marco back in 2008. This thing was so small, its wind field was barely wider than some big cities.
Really? That's tiny for a cyclone.
It was incredibly small. But then you've got the giants, like Typhoon Tip, which was so massive it could have stretched across the entire United States. Can you imagine?
Across the entire U.S. That's mind-boggling.
It was a monster storm. Actually holds the record for the largest tropical cyclone ever recorded. Typhoon Tip.
Wow. So we've got these tiny cyclones and these absolute behemoths. Does size have anything to do with how dangerous they are?
That's the thing. Size isn't everything. A small cyclone, it can actually be a lot more intense when you look at wind speed.
So it's not about how big the storm is overall, but more like how much of that power is concentrated in the center, the core. Yeah.
Exactly. It's like, think of it like a campfire versus a blowtorch.
Yeah.
Both of them, they generate heat, but that intensity, it's on completely different levels.
Right. One's concentrated, the other's spread out.
Exactly.
Makes sense. Okay, so we've got these swirling masses of energy, big ones, small ones, forming over warm ocean water. But how do they decide where to go? It's like they have a mind of their own, these cyclones.
Well, they are influenced by something we call the steering flow. Basically, the wind currents up in the atmosphere.
So they're guided by the wind, kind of like a sailboat catching a breeze.
Yeah, that's a good way to think about it. But here's the thing. It's not just the wind pushing them around. Even without that, cyclones, they have this natural tendency to drift westward and kind of towards the poles.
Really, even without the wind, they just drift on their own.
Yeah, it's called beta drift, and it all comes down to the Earth's rotation.
Wow, that's wild. It's crazy how these storms are affected by forces on such a huge scale.
It's pretty incredible, and it gets even more interesting. Imagine two cyclones get close enough to each other, right?
Oh boy.
Things can get pretty wild. We call this the Fujiwara effect.
Fujiwara effect.
Yeah, so basically, when these two cyclones get close, they start to influence each other's movements.
So they can collide.
Kind of. Sometimes they dance around each other, swirling and twirling. And other times, well, one might just absorb the other one.
Like a cosmic dance-off.
Exactly. And nature can be pretty amazing to watch.
Beautiful, but also terrifying, right? I mean, we've been talking a lot about the destructive power of cyclones. But the article, it also mentions some surprising ways these storms can actually be beneficial for the environment.
Yeah.
It's like, wait a minute, these giant storms can actually be good.
It really shows you how everything's connected, Like one of the things cyclones do is bring tons of rain to places that really need it, like those drought-stricken areas.
Right, right.
That rainfall can be a lifesaver, literally replenishing water sources, helping those ecosystems bounce back.
Nature's way of evening the score.
Yeah.
So it's rain. What else?
Oh, yeah, they're like giant heat pumps, these cyclones. They move heat around, taking it from the tropics and carrying it towards those colder poles. Like a global AC unit, you could say.
Wow, a global AC unit. That's one way to look at it. And remember how we talked about cyclones churning up the ocean?
Right, right.
Well, the article mentioned something about nutrients and how that churning actually helps.
Oh, absolutely. When a cyclone comes through, it churns up that deep ocean water, brings all those nutrients up to the surface, and you know what that means. It's like ringing the dinner bell for phytoplankton, which are like, well, the bottom of the food chain in the ocean.
So everything gets a feast, thanks to the cyclone.
Exactly. Nature's buffet. But, it's not all sunshine and roses. The article also mentions some downsides to all this churning.
Right, because stirring things up can be, well, messy sometimes.
For sure. Cyclones can bring up some nasty stuff, too. We're talking pollutants, stuff that's been sitting on the seabed or along the coast, gets churned up by a cyclone, ends up contaminating water, messing with those ecosystems.
So it's like they're digging up things that were better left buried.
That's one way to put it. It's a good reminder that the effects of pollution, they can last a long, long time. And cyclones, they just bring those consequences to the surface, literally.
That's a powerful image. Speaking of consequences, how do we even know what these cyclones are going to do next? The article talked about tracking and forecasting them, and it's amazing how far technology's come.
It's pretty mind-blowing. It's a mix of the old and new. I mean, we still get basic info from ships out at sea, weather stations, but now we've got those satellites up in space, keeping an eye on things, and then those supercomputers crunching all that data. It's remarkable.
It really is. But the article, it also said that even with all that tech, figuring out how strong a cyclone's going to get, that's still a huge challenge.
Absolutely. Predicting intensity, it's like, well, think about trying to bake the perfect cake, right? There are so many different factors, so many variables that can change how it turns out. Cyclones are the same way.
So how do scientists even try to get a handle on a cyclone's intensity?
They've got some tricks up their sleeves. One is called a dropsonde. Basically, it's like a little mini weather station.
A mini weather station.
Yeah, they drop it out of a plane right into the heart of the storm. Talk about getting up close and personal.
That's intense. What kind of info do those things even collect?
They're little data ninjas. They measure everything. Temperature, humidity, pressure, wind speed, all that good stuff. All from inside the cyclone. Gives us a real-time look at what's going on.
Wow, that's incredible. So we're getting better at forecasting, but it seems like we still have a lot to learn about these powerful storms.
Absolutely. And the stakes are getting even higher with climate change and all. Warmer ocean temperatures, they could lead to even stronger cyclones in the future, which could impact even more people and ecosystems. It's something we need to keep studying and understanding.
It's a lot to think about. Well, this deep dive has been eye-opening, to say the least. We've covered everything from the birth of a cyclone to its impact on our planet, and wow, talk about a crash course in meteorology.
It's a fascinating field and crucial for understanding our climate.
It really is. And to our listeners, next time you see a storm brewing, whether it's on the Weather Channel or maybe even out your window, remember what we talked about today. Until next time, stay curious.